Alright, welcome back. So we're going to try one more day of this process where you watch a video, try out the stuff on your own. If you have questions, come see me in the back. Right now we're looking at the homework that we reviewed in class. And then here is what we talked about yesterday. So just to review, a trapezoid is an equilateral with exactly one pair of parallel sides. The parallel sides we call the bases, and the sides that are not parallel we call the legs. And then this was the difference between what we are used to with isosceles and what we are now seeing with trapezoid is, right, we said yesterday, we usually see that the top and the bottom are our bases. So the angles that we call the base angles have to be consecutive, but there should be one on each base. So these two right here would be one pair, and these two right here would be another pair. We're going to talk about base angles a little bit more today than we did yesterday, so that's why I wanted to go back over and stress that. So if we go on to the next one, we did this one yesterday as well, and we learned here that when we have our median of a trapezoid, which here is MN, that will always be parallel to our bases of our trapezoid. And along with being parallel, we can find the distance of MN by taking the average of our two bases. So if we look at that, we saw that in our exit ticket yesterday of how we can use this equation down here to find out a lot of information. I might give you the median and give you FG, and then you actually have to find the number for EH or find X and so on. So we reviewed our exit ticket as well. I graded that and passed it back to you. So hopefully this is making a little bit more sense to you now than it did yesterday. In the video we also looked at this, so if you got that far in the video, that's good. If you didn't, go back and watch that, because we're going to be building off of this idea of now we can use our angles to help us try to figure some stuff out. So we did not get to this check your understanding yesterday. We're asked, how does a trapezoid differ from a kite? And in a kite, we know we never have parallel sides, but in a trapezoid we do. If we want to take that further, there is no way for there to be consecutive sides that are congruent and also for there to be any parallel lines. Once we start doing those things at the same time, we get a whole different type of shape. And then, can a trapezoid have bases that are congruent? So let's actually try to figure that out. If I make a trapezoid, we need two line segments that are parallel, and here we want those bases to be the same length. So there I drew one base, and there I drew the other. When I do that, I can say these are the bases by putting that arrowhead there, and now I can connect those to make a shape. When I do that though, our bases were congruent, so thus we can put our congruent tick mark, but now we can see that there's something else going on in this shape. What might be going on? Right, there's something else going on with these green lines, our legs. Our legs are which ones we said that were not parallel. If we look at this, they're looking like they might be parallel. We can take this a step further and draw one of our diagonals. And since these are parallel, we can use our corresponding angles postulate to say these are parallel, and this would also be congruent to itself. So we would actually get a SAS congruency postulate here. And we could prove that these two triangles are congruent, which means that our sides here are congruent, our legs, And we could then keep going and say that they're parallel to each other as well if we did a converse of the corresponding angle postulate. So now we have two sets of parallel sides. So that's a totally different shape now than a trapezoid. Hopefully you can figure out what shape that is. I'm not going to say it in this video. So hopefully you can figure out, if we have two sets of parallel sides, what shape we actually have. But we're going to move on to our next slide, and I'm going to zoom in for this one. Alright, we're going to start talking about something called an isosceles trapezoid. So an isosceles trapezoid is when we have a trapezoid with congruent legs. In our last example, we also had that, but usually with an isosceles trapezoid, right, our congruent sides don't go in the same direction. They actually point towards each other. So that way we still have a trapezoid where the two legs are congruent to each other, but we don't end up with the scenario we saw on the last slide. So when we start looking at this, they use an isosceles triangle ABC, right? This triangle right here is triangle ABC, and we're saying that's isosceles since AB is equal to CB. So we're going to use this isosceles triangle and then find an isosceles trapezoid inside of it. So when we do this, we're going to go through this pretty quickly. You can jump ahead to the next part. We're doing this just kind of to understand what's going on, not necessarily going over any notes here. This is just going to kind of help us understand why what we're going to get to on 7F is true. So if we walk through this, we're saying that AB is equal to BC and that AD is equal to CE. So these parts are equal to each other, and then this whole side is equal to this whole side. It's not really a good way to mark that up, so I'll just put those brackets there. The book wants us to figure out what angle is congruent to angle A. We know very little about this triangle and this diagram besides that we have an isosceles triangle and these pieces are congruent. So hopefully by the fact that it's isosceles, we remember that our base angles would be the same in an isosceles triangle, and for isosceles triangle the base angles would be angle A and angle C. So those would be congruent, and that was because of the isosceles triangle theorem. That stated that if we have an isosceles triangle, our angles are the same. Alright, so now we can scroll down. We want to explain why the smaller triangle would also be isosceles. So this one will take just a little bit of explaining. Here we know that AD is equal, I'm sorry, not AD. We know that AB is equal to BC. That was given to us. We can also break down AB to its two parts to say that AD plus DB, right? So we broke down AB, so now let's break down BC is equal to CE plus EB. Alright, so we can then use that second piece of information, what's in the red box at the top, that AD is equal to CE, and we can just do this in a quick way. We can cancel out that information. So since they're equal to each other, that means that DB and EB must also be equal to each other, since we can subtract those two pieces out. So we get that DB is equal to EB, which means that this is equal to this. So which means that this triangle is isosceles. So if we scroll down, now we want to figure out, why would AC be parallel? Well, what would AC be parallel to? We only really have one other line that you would even go in a similar direction as AC. So we can fill that information in, and we could say that that should be parallel to DE. That's the only option that we have, because everything else is clearly not parallel to it. So we want to somehow prove that these two lines are parallel. We have a lot of options now. We know so much more about this diagram. But namely, we have these two isosceles triangles. So we already know that A and C are congruent to each other. By the same reason, we can say that D and E are congruent to each other. All right? But we need to think, in order to prove these lines are parallel, somehow we need to prove, just as an example, that D and A are congruent to each other. The only way to do this would be to say, since both of these triangles are congruent, are isosceles, angle D plus angle D plus angle B adds up to 180. I put D twice because D and E are the same thing, and then likewise on the bottom, A plus B, this is now for the bigger triangle, equals 180. Alright, so now if we notice this, B's in both, so we can kind of cancel that out, and then 180 is in both, and then we also have two A's being repeated. So that kind of shows us that A is, the measure of angle A would be equal to the measure of angle D. When that's the case, these two angles are congruent. We can use, technically, I'll try to write this very small, the converse of the corresponding angles postulate would prove that these two lines are parallel. So now that we know the two lines are parallel, we want to show that the quadrilateral ADEC, which is that bottom quadrilateral, is in fact an isosceles trapezoid. This one's going to be pretty quick. We do know, we already proved that AD is equal for sure to EC. We showed that that was given to us, right? We didn't have to show it. That was given to us. That's one part of being a trapezoid. That's the isosceles part of being a trapezoid, but we need the actual trapezoid part, which is saying that we know that two sides of that shape are parallel, and we just proved that those two lines are parallel. So we do know that AC is parallel to DE. So by piecing together part B and C, we can say that that is an isosceles triangle. And then since it's an isosceles triangle, we could use what we already know. Not what we already know, but we can use what we know about our isosceles triangles that we already marked up here, that to say that ADE is congruent to CED. So let's take a look at that. I'm sorry, I keep moving around. I'm going to erase some stuff just so we can see it a little bit better. What we're trying to prove right now is that ADE is congruent to CED. And we know that these angles are congruent, so since they're both linear pairs, their components also have to be equal to each other since they are equal to each other as well. All right. So if we keep going down, that means all these things are congruent to each other. So the base angles and isosceles triangles will be congruent. So if you skipped ahead in the video, hopefully you landed here. Alright, there's no way I'm going to fit it on that line. So the base angles of an isosceles trapezoid are congruent. So we'll see an example of that when we actually use this on the next problem. Let me just circle this a couple times so that way people who are trying to skip ahead can realize that this is important. Alright, the base angles of an isosceles triangle are congruent. That means, for example, if this angle right here was 100 degrees, by this theorem, this conjecture that we're making, this angle right here would also be 100 degrees, which means this one would be 80, which means this one is also 80. So we can now use that if we know it's an isosceles trapezoid. We can now do some stuff with angles. Alright, so now let's move on to the next example. Which we're going to do a little bit of real work here to actually do this. So we have a graph at the bottom of this. We're going to plot these 4 points for the quad cold, C-O-L-D. And then we're going to see, is that in fact an isosceles trapezoid? And if so, we're going to try to discover one more thing about it, which we can see down in D. Alright, so let's jump down to our graph. Alright, so let's start graphing it. At the top of this, which you should see in your book, we know that C is 1, 0. We know that O is 2, 2. We know that L is 5, 3. And we know that D is 7, 2. Alright, so if we connect these lines carefully, we can start to see the trapezoid start to form. Oops, the quadrilateral start to form. So this is what it would look like once we graph it. What we need to show next for part A says to show that this is a trapezoid. It does look like it. If we remember from yesterday, we did this. We need to prove that to be a trapezoid, we need to prove that this line is equal to that line. Alright, to prove that, we need to show that our slopes are the same. So let's do that real quick. Alright, the slope, we're going to look at OL first. We'll use L as x2 and y2. So that would be 3 and then 5 for x at the bottom. And then O is our would be our x1, y1. So we would subtract our y value, which is 2, and then subtract our x value, which is also 2. So for this, we get 1 over 3. No need to reduce here. So we're good. Let me color in the bottom one different, so that way we can change our colors up and know what slope we're finding. So the slope of CD, we can do so in the same way. So we can do our y value of D minus our y value of C. Those aren't the y values. Our y value of D minus our y value of C divided by our x value of C minus our x value of C. So here we get 2 on top, 6 on the bottom, and we can simplify that What does that simplify to? Yep, 1 over 3. So our slopes are the same. So that means these lines are parallel to each other, which means we do have a trapezoid. So 8 part A is good. We do have parallel sides. So we have a trapezoid. We should also double check that the other sides are not parallel. We can do that as a quick visual check. If they were looking like they might be parallel, we should go in and find the slope of this, but these are very obviously not parallel, so we can move ahead. 8 part B says prove that quad cold is an isosceles trapezoid. So now for that, we have to prove that our two sides are the same length. So to do that, we need to use our distance formula. Let's start with OC. So unfortunately, unlike yesterday where we could find some shortcuts, here we have to do it the long way. So it's still y2 minus y1. So we would do 2 minus 0 as our y values, plus, and then x2 minus x1. So we did 2 as our y2, so we need to do x as our x2, 2 as our x2 minus 1. We would square it. So we can now start to simplify. So we get 2 squared plus 1 squared. That would equal 4 plus 1, which equals the square root of 5. So let's see if we get the same thing for LD, which I'm sorry if you can't see the yellow on the white too well. I'll switch to black. So now for LD, we will get, let's just choose D as our second point. So we would do y2, which would be 2 minus 3 squared plus x2, which since D we said as our second point, that would be 7 minus 5 squared. So we get 2 minus 3, which is negative 1 squared plus 7 minus 5, which is 2 squared. So inside our radical, we get 1 plus 4, which if you don't believe me or not, or didn't see it in the picture or not right away, we do get that these two sides are equal to each other, so that does mean that we have an isosceles trapezoid. So now that we got to the most important part, I ran out of space. So now let's unfortunately have to erase the work, and let's try to find the next step, which says find the length of each diagonal of our trapezoid. So let me go in and clear up our space. Oops, went too far. Ugh. Alright, let's clear up our work. Alright, so now we want to find the lengths of our diagonals. So the first diagonal we have would be OD. That looks like it's a straight line, so we can do that one pretty fast because it's not, it just has a slope of 0. We can just actually count the distance here. 1, 2, 3, 4, 5. So the distance of OD is equal to 5. If we use the distance formula, that's fine. We would just get to 5 at the end of it. Next, we can find the distance of our second diagonal, which would be LC. So if we do that, we do have to use our distance formula here. So we can choose L as our second point. So we can start with Y. So 3 minus, and then the Y value of C is 0, squared, plus, and then we would do our X value of L, so 5 minus 1 squared. So we get 3 squared plus 4 squared So we get 9 plus 16. So we get the square root of 25, which means we get 5, which means our diagonals are the same length. By doing it for this one example, we can see what's going on, so we can actually fill in 8 part D with at least a response that says, based on the results for this one trapezoid, we can complete the theorem below to say the diagonals in an isosceles trapezoid are congruent. Right, they're both equal to 5. They're equal to each other, so they are congruent. Alright, so that is all that work, and I erased most of it, so we are doing some lengthy stuff here. Number 9 goes in and just says, what we just didn't really prove it. It was just to build up a conjecture. So now let's try to figure out how could we prove that the diagonals always have to be congruent to each other. So now we have to use, in some form or another, some theorems or postulates to actually build up a new theorem. So we're going to do this one quickly. We know that core is a trapezoid, and we know that CO Alright, looks like my pen has stopped working, which is odd. Now it has. So let's see if I can zoom in. Okay, so took me a little too long to get it to work. So CO is equal to ER, which means what type of trapezoid do we have? Right, that means we have an isosceles trapezoid. We want to prove that the diagonals are congruent to each other. So we have to use some other properties of the trapezoid that we've already proven or that we know already. So we know, because it's a trapezoid, we know our two bases are parallel. So if we look at this, we might have to use that. We also know that our base angles are congruent to each other, so we can add in these as well. So we're starting to form our diagram with a lot of information in it, maybe even too much information, so we can kind of know what we just did, and we can just use only the helpful information. So probably the one that they give us is going to be good. These are congruent to each other. The only way to really do this is we want to show that CR and EO are congruent. So let me highlight that in just a darker black. We can see almost something that's going on with our diagonals and the lines that were given to us. We have two sides of a possible triangle. So we could go in and finish out our triangle. So we have this green triangle right here, and we have this red triangle right here. If we prove that those two triangles are congruent, then we can show that our diagonals are congruent. So we already have a lot of information here, right? We have that our legs are congruent. We can say that this side is congruent, so we have two S's now. So we can either somehow prove that the diagonals are already congruent to each other, which we said that's what we're trying to prove, so that's probably not what we're going to use. So we are not going to be able to use SSS. So remember, we also have SAS and ASA, or HL, in order to prove this. Or we could use AAS. We already have two S's, so let's try to shoot for SAS. We need to then know that these two angles are congruent to each other. Do we know that? Yes, we do. We proved that on one of our other slides. So we know that these two angles are congruent to each other. So we can say SAS right away. to show that the green triangle is congruent to the red triangle, which means that our diagonals are congruent to each other. So that proof wasn't too bad since we didn't have to write it down, so hopefully you understood it as I said it. If you didn't understand it, all you have to know is what we wrote on the other slide, which was that the diagonals of an isosceles trapezoid are congruent. Does make sense because we talked about it, sort of an overview of the proof, but didn't do the proof. So as a last little check-in for the check your understanding, we were given another quadrilateral plan, PLAN, and we're told that it is an isosceles triangle. So if we start to look at this, right, they said it was an isosceles triangle. So let's try to use some of those properties to do the following. LPN, so LPN would be this angle right here, would be congruent to which angle? So we can just look at that visually or just use our theorem to say it would be equal to the base angle that's congruent to it. So that would be the other side, which would be angle L. But since there's a lot of other angles at angle L, we would put that in the center and just use the points that are on either side of it. So PLA, or we could even say ALP. They said that angle PLA was 70 degrees, and they want us to find out the other one. So LPN, we just said those were congruent, so we can fill that in right away. But now it's asking us to find PNA, which let me change color, which would be this one right here. How could we figure out what that one is equal to? Right, we said this angle over here would also be equal to 70. How could we figure out what N is? Right, if you recall, we talked about this in the last video. Since these two lines are parallel, that means these two angles are supplementary. So that means that angle PNA has to be supplementary to 70, which means it would be 110. All right. Likewise, we can use one of our new theorems, write an equation and solve for x if AP equals x and ln is equal to 3x minus 8. So let me clear up our space, our diagram. So AP is this line segment right here, and NL is this line segment right here. What are those? Yes, they're the diagonals. What type of trapezoid do we have? Yep, we have an isosceles trapezoid. What do we know about the diagonals of an isosceles triangle? Yes, they are congruent. So that means we can write this equation that AP, the distance between A and P, has to be equal to the distance between N and L, which means we can say that X, because that's what AP is equal to, has to be the same thing as 3X minus 8. I'm going to leave that for you to actually solve for X. You guys are fully capable of doing that on your own. You don't need me to do that in the video. So your homework tonight is going to be just these two problems where we have numbers up and top for 11, and you can find these three line segments, QU, VS, QU, VS, and UV, which is all just numbers. And then 12, I'm going to step it up, and I'm going to give you some stuff with expressions in it. Make sure you notice that we say an isosceles trapezoid here, so we can use that to figure out X and Y, and then use that to figure out what all of our sides and line segments in this diagram are. So good luck on the homework. I have yet to determine when I want that due. I'll have that determined for you in class. So good luck.